Well, all right. It's time to get started, folks. Hopefully, I'm still sharing. Maybe. Nope, not sharing. One
Oh, we see your
second.
screen.
You do? Okay.
Yes.
You're seeing that now?
Yep.
Okay, great. All right. Well, we'll get underway, and I think folks will be shuffling in still. It's, you know, probably don't everybody doesn't probably don't want to see all these announcements. But for anybody who doesn't know me, I'm Chris Wenzel, the current president of the LIAPG. And, thank you for showing up for this presentation tonight. These webinars over the last 12, 16 months have been going quite well. And we've had a number of excellent speakers, and I have no doubt that tonight will not disappoint you. So a little business to get out of the way before we get started. And we'll move right through this. Fine. Okay, so um, we'd like to thank our corporate sponsors that we've had in the past. Um, we don't have a list for 2022 yet. We've been having some trouble with our website in getting renewals done, but we will work that out. But our past, consistent sponsors have been at the diamond level, Cascade Environmental Drilling, PW Grosser, at the Topaz level, Alpha Analytical, EnviroTrack, ERM, Island Pump and Tank, Regenesis, VHB, and York Analytical Laboratories, and we appreciate your supporting us. It really goes a long way to help us. And for anybody who's attending, if you're interested in knowing more about these organizations, you can go to the LIAPG website, and there is a scroll of our sponsors. And if you click on their logo, it will link you to their website, and you can check them out further. We'll talk about some upcoming events. We've had having these Zoom meetings and trying to have them every month, and they're typically the third Thursday of every month. And we are perpetually looking for speakers and good varied content of some geological and or environmental topic. Next month, on the 21st of April, we have Jane O'Connell from New York State DEC speaking on proposed revisions to the Part 375 regulations. That should be a good one. And then the 19th of May, we have speaker Caitlin Ahrens from NASA, and she's going to be talking about the topic. The title is Mysterious Marvelous Cryogeology. And what I had asked her to do was make a presentation on the interesting geology of the moons of the outer planets like Jupiter, Saturn, Pluto, and their moons. So I think that's going to be a good one also. There's a lot of amazing geology just in our solar system that we've just begun to study. Everybody's heard about Mars, but there's so much more. We don't have any speakers for June and beyond. So please, if you have something interesting and you're willing to give us a presentation, we'd sure love to hear from you. We're also planning some field trips local to the island. Stay tuned for that. You'll see announcements. The LIAPG board meets monthly, usually the first Monday of every month, and it is an open forum. And anybody who's interested in getting involved, helping us bring some of these things to life as we go through the year, just get in touch with us. You can email us at ligprez@gmail.com. It's on our website, but if you want to check it out, we're happy to have you. Right now, it's still been online. We'll see about a face-to-face forum coming up in the near future as things get better. Some other things going around with our other New York State and regional associations. You've got the New York State Council, who we all are represented on the board there, and they have put together, as you know, with the professional geologist licensing, you have to get a certain number of hours of professional development time. The council has been authorized by the state education department to manage that, and so you will see in the future, LIAPG presentations qualifying for professional development hours. There is a a presentation. It's going to be a multiple days put on by Midwest Geosciences that the council has arranged for. It will be a pay event. I think it's 3 sessions of about 150 minutes, but it's called Challenges and Strategies for Implementing Environmental Sequence Stratigraphy. And it actually provides 8 professional development hours, which is pretty awesome. I believe it's within 3 years, you have to have 36 hours. So, you know, check it out. Buffalo, BAPG, 28th of April, they've got an annual enrichment seminar that has, I think, 5 topics. I know one of them is about the Part 73, 375 changes, but there's some other good stuff there also. You can check out their website. Central New York, Paul Harnick from Colgate is going to be talking, and it listed the topic as TBD. That's on the 13th of April. You can check that one out on their website. Same thing, Humpka didn't have anything listed, but their website usually does, produce the announcements. The Northeast chapter of the American Institute of Professional Geologists, same thing. There was nothing listed, but if you check out their websites, you'll see that things do get posted. We've been featuring, Pennsylvania Council has a fairly robust program where they are able to schedule things out for several months at a time. And some of these you saw in our December presentation, hydrostructural methods and bedrock aquifer characterization, essentials of borehole geophysics, factors affecting groundwater quality for domestic supply in the Marcellus Shale. And there's a presentation on in situ remediation of sulfate contamination. Some of these are pay for non-members, but if this content interests you, check it out. The also at SUNY Stony Brook, there is a geology open night lecture series that occurs, and the next one's on the 25th, and I believe the topic is on if I'm not mistaken, and returning samples from Mars. It's talking about the program to right now. The rover is collecting soil samples and stashing them, but that should be a good one. So check it out. You were going to say something, Jen?
Yeah, I was just going to tell you what the topic was, and it's
okay.
By Professor McLennan.
Gotcha. Okay. ASBOG exam for professional licensure. The March exam was, I think, the 18th of March, just the last week. But upcoming, offered twice a year in October and March. You can see the application deadlines there. So if that's something on your radar, pay attention to the deadlines. There is a certain amount of effort that goes into preparing your applications. So you need to start that in advance of the due date. And Gil Hansen's conference on the geology of Long Island and metropolitan New York that is on a Saturday every April. We're up to 29 years now, and that's going to be an online event. You can check out the Long Island Geologist website, and the list of presenters and topics is posted at this point, and it's going to be a good one. I've always enjoyed it, tried to make it every year. Not every year have I made it, but I really enjoy going. I've always enjoyed seeing people, the same, hardcore geologists year after year, and the topics are great. The presentations are short and with a Q&A at the end, so you can sit there and in 2 or 3 hours you can get a lot of good content, and it's really enjoyable. So check it out. And
Chris, it's now, April 9th, not April 19th.
It's April 9th?
Yeah.
Uh-oh. Well, thank you. Appreciate that, Dennis, very much. It's April 9th. And actually, if you're on the email list, you should have gotten that announcement this past Tuesday. And with that, we're going to go to the main event, and Dr. Glotch from Stony Brook has been kind enough to offer his time to make a presentation tonight on the Lunar Reconnaissance Orbiter that has been orbiting the moon for quite some time and doing some really amazing mapping. That data has been looked at, processed, analyzed, and it's going to be used for the next phase of exploring the moon. So I'm going to stop talking. I'm going to stop sharing my screen, and Dr. Glotch will let you share and take it away. So thank you,
All right.
welcome, and thank you in advance.
Thank you very much, Chris. Appreciate it. Let's see. I'll try to share here. And I'll just say before I get started, actually, I saw you have Caitlin Ahrens coming up for a talk. I know Caitlin, and I've seen her give a bunch of talks, and she's fantastic. So highly recommend her presentation in a couple months on cryogeology. It should be pretty awesome. Let's see. I will share from the current slide. So I'm very happy to talk with you tonight. I've been working on the Lunar Reconnaissance Orbiter mission for more than a decade now. And this spacecraft has been a real workhorse for solar system exploration since 2009. Being involved with this mission has completely changed the course of my career and the work my students and I have done. And I'm kind of profoundly grateful for all the work that the scientists and engineers at NASA that have made this mission a reality. And so what I kind of wanted to do was talk about some of the big highlights that have come from Lunar Reconnaissance Orbiter, which I'll just refer to as LRO for most of the talk. And then kind of towards the end, I'll talk about how this mission, which is now again, spacecraft's more than a decade old, is really setting us up, kind of like Chris said, for the next phase of robotic lunar exploration and also human exploration of the moon. NASA's in the process of planning to send people back to the moon for the first time in more than 50 years. And it's really exciting, and it's really cool to be kind of part of that process. Okay, so LRO is, we've been kind of, looking at the moon for more than a decade. And, we learned a lot during the Apollo era. So when during the 60s and 70s, we sent astronauts to the moon. So everything we learned, though, our view of the entire body of the moon as kind of like almost a planet was pretty limited, for, what we, for the areas that we explored, we explored a total surface area smaller than New York City. And so, you wouldn't be able to be a Martian and come to Earth and explore New York City and tell me everything you needed to know about Earth and how it formed and, how it got there and how it evolved over time. And the same is true for our exploration of the moon. What LRO has given us is kind of a global picture of the moon as a planetary body, and a much better understanding of how it formed and evolved over time. We are sending humans back to the moon as part of the Artemis program. And for that, we require a baseline data set to show safe and scientifically interesting places to explore. LRO has helped there. And now that we've been investigating for the moon for more than 12 years with LRO, that's actually a nice long duration mission. So we can actually start to understand how the moon changes on human timescales. The moon is not geologically dead. There's a lot going on. It's a dynamic surface that interacts with the space environment. And we're able to view those changes over decadal timescales now with this vast data set that has been built up by LRO. And then again, with the Artemis program, sending humans back to the moon. Artemis is the sister of Apollo. So the Artemis program is the follow-on to the Apollo program. We're going to be sending humans to the South Pole of the moon as early as 2025, and some robotic landers as well. So exploration of the South Pole is a major goal, and it's a new objective that LRO is currently helping out with. What you're seeing in this picture on the right here is the actual LRO spacecraft before it launched. And then these instruments these labels here are different instruments that are on the LRO spacecraft. LROC is the Lunar Reconnaissance Orbiter camera. The WAC is the wide angle camera, which takes pictures at a couple hundred meters per pixel spatial resolution. There's also a NAC, or a set of narrow angle cameras. Those are essentially our spy cameras in orbit around the moon that take pictures of several tens of centimeters per pixel that are, we can actually image the Apollo landing sites. The LOLA is a lunar orbiter laser altimeter. It's a LiDAR instrument, essentially. LAMP is an ultraviolet mapper. LEND is a neutron mapper, which tells us about water on the surface of the moon. And Diviner is an instrument I'll be talking about a lot. That's the instrument I've been working on for a long time. It's an infrared radiometer. So it's essentially like a very fancy thermometer that can map surface temperatures on the moon, but we can do that at multiple wavelengths, and we can actually get compositional information from that. So that's actually what I'm quite interested in. And a lot of work I've done has been mapping the bulk silicate mineralogy and rock types on the moon using this Diviner instrument right here. And then this mini RF instrument is actually a radar instrument that we use to map the moon as well. Okay. All right, so these are the instruments I just talked about. LRO launched in June of 2009. So there's another instrument I didn't mention called Crater. Has nothing to do with mapping craters on the moon. It's actually a radiation environment, and we've learned a lot about how the sun and the solar wind and the cosmic rays interact with the moon by measuring the radiation environment around the moon. Diviner is for thermal and compositional mapping. LAMP is an ultraviolet and water mapper. LEND maps neutrons and hydrogen, which tells us about water on the surface. LOLA gives us topography. LROC gives us high resolution images. And mini RF is radar and ice mapper. Okay, pardon me. So we can think about LRO and the niche that it fills by thinking about the moon and our exploration of the moon in terms of time and space. So the Apollo astronauts, when they visited the moon, they left experiments on the surface. Those Apollo Lunar Surface Experiment Packages, or ALSEPs, they give us information about very kind of local or regional scales of the moon over diurnal or daily timescales. We've also sent short duration landers, which give us a really local snapshot of the geology of the lunar surface over the same kind of like diurnal or shorter timescales. And when I say diurnal on the moon, that's actually about a month, right? So the moon rotates on its axis for every revolution around the Earth one time. So one lunar day is about a month of our Earth time. And so, we've done kind of local and regional experiments. There's a spacecraft called LIAPG, which was measuring the lunar atmosphere and exosphere, which gave us some information at kind of regional scales and diurnal time scales. And then a previous spacecraft called Clementine was in a fixed orbit around the moon. It gave us global coverage of the moon at essentially kind of one time a day, based off of where in its orbit it was. And so it kind of filled in this space up here, gave us global coverage, but over a very short time scale. LRO kind of fits in way up here, right? So it gives us global coverage over the entire lunar day. Over time, it kind of builds up a data set, but then also over decadal timescales, right? So it's been at the moon for more than 10 years. And so we're viewing changes over daily timescales, and we're viewing changes over decadal timescales. And some of the things we've been able to see are actual identification of changes on the lunar surface. I'll talk about some of those. Variations in how the daily or the kind of decadal timescale of the solar minimum and maximum affects the lunar environment. So variations in the solar and galactic environment over time. Regolith thermal physical properties. When I say regolith on the moon, that's kind of a fancy word that planetary scientists use for soil to not make soil scientists angry at us for calling the lunar dusty stuff actual soil. So the regolith, the kind of broken down, fine-grained material that covers most of the lunar surface. We can actually measure changes in temperature over time, which tells us those physical properties of those materials. And then we can measure global temperature variations, and that tells us something as well about the physical properties, including the density and porosity of materials on the surface. So I'll kind of go over some of a bunch of these examples. So LRO also provided a bunch of firsts. So we found, if you go to Hawaii Volcanoes National Park and you hike around, you can actually find these big holes in the ground, these big pits that are essentially skylights to lava tubes. We've actually found those on the moon with LRO. There are these features like this area down here in the bottom image called Ina D, which is what we call irregular mare patches, which might be very young for the moon volcanism. Volcanism on the moon that's less than 100 million years old. We're used to thinking, the canonical view of the moon is that it's a geologically dead body. We haven't had any volcanism on the moon for 3 or 4 billion years. These imps are potential evidence for very, very young lunar volcanism. There are these craters on the surface that are a few degrees colder than everything else around them. And I'll talk about those in a little bit and what those tell us about the generation of this regolith on the moon and kind of development of kind of the typical lunar surface. And how we can use temperature measurements to tell us about that. And then we've measured the actual kind of impact cratering rate in the solar system today by seeing new craters form on the moon as well. We've made some first geophysical measurements of the lunar solid body tide, which tells us about the lunar interior. Ultraviolet and far ultraviolet maps of the lunar surface, which have been able to map water frost in some areas on the moon. The moon is not bone dry. It's actually, we've found ice at the poles, and we found kind of monolayers of water throughout the lunar surface. And then we've got the first kind of high resolution global radar properties of the moon from LRO as well. For a long time, we thought the moon is basically composed of essentially two rock types: basalt, basically the same material that's Earth's oceanic crust, and anorthosite. But we've actually found evidence, and this has been a lot of my own work, for evolved magmas, things like rhyolites and granites on the surface of the moon. We've found evidence for surface volatiles that are vary spatially and laterally and temporally. There's a process that occurs called space weathering on the moon. That's all about the interaction of the space environment with the lunar surface that we've been able to measure at the best resolution ever with LRO, measured the exospheric dust environment and the radiation environment as well. So lots of firsts over this decade of science from the moon. Okay, so here you're looking at an animated GIF of a new crater forming on the moon. It's at 34 meters in diameter. This is 2 images taken, relatively, short timescales, apart. And, we've actually measured, a bunch of these, over the surface of the moon. So these are, real surface changes that are occurring. So this little crater you're seeing here, that's 34 meters in diameter, that's one change that you're seeing. But notice that the brightness of the lunar surface is changing substantially as well. This is the impact ejecta, the material that's excavated by that impact and thrown out over the surface and forms these rays that can extend for tens or up to 100 crater radii away from the surface. And so the lunar surface is constantly being modified by impacts large and small. We've also been able to measure changes to the lunar surface that humans have caused. And so my colleague Ryan Clegg, she has used the Lunar Reconnaissance Orbiter camera to look at some of the Apollo landing sites. And what you can actually see are these little dots, these little bright dots that are each of these arrows are pointing to. And these are the actual hardware that we use to land astronauts on the surface. We can image that from orbit. And what you'll notice is that all of those areas around the surface are bright. That's because as those landers descended onto the lunar surface, they used rockets to slow down, and those rockets churned up the regolith and churned up the soil, and they changed the optical properties of the soil so that they actually appear brighter and they reflect visible light more. And so we've been able to map these blast zones around the lunar surface. And this work has actually turned out to be really important as we're planning the next human missions and the next rover missions to the lunar surface, because we want to be able to sample and understand pure, unadulterated lunar regolith. And what these images tell us and what these images give us is a sense of how big these blast zones are and how far away we have to go from the landers to sample material that's never been disturbed over billions and billions of years. And so here are a bunch of the Apollo landing sites that you see on the left. But the US is not the only country that has landed on the surface of the moon. What you're looking at on the right is an image of the region on the far side of the moon where the Chinese landed the Chang'e 5 lander. This is a lander that grabbed a sample of the surface of the moon, put it in a capsule, and launched it back to Earth. And this is the first robotic sample return from the moon since the Soviets did this with the lunar rovers in the 1970s. And it's the first samples returned from the moon since the Apollo astronauts brought samples back in 1972. So I'm going to show some of the types of data we can get from LRO. And so here's a movie composed of lots of Lunar Reconnaissance Orbiter cameras. And so this is a set of high resolution imagery of the Apollo 11 landing site. You can see the rover or the lander here. You can see, let's see here, let's keep going here. You can see these dark streaks here that I'm pointing out with my cursor. Those are the footprint tracks that the astronauts, Buzz Aldrin and Neil Armstrong, left on the surface of the moon. We can actually image from orbit the tracks left behind by Buzz and Neil as they were walking on the surface of the moon. This is just amazing to me, right? And you can kind of see when we can take images from different angles and put them all together, we can get these oblique views that give us a good sense of the topography. And so you can see, all of these little craters, all and some quite large craters around the area where Apollo 11 landed. Neil Armstrong, as he was piloting the Apollo 11 module down to the surface, he was trying to avoid all these things and land in an area that was flat. And so he had to actually take manual control. The initial plan was to land robotically using a guidance computer, but he actually took control to avoid landing in some of these larger craters. Here you can see the Apollo 15 site, Hadley Rill, where the astronauts landed and explored this lava channel that's called Hadley Rill, and this mountain formation, which is thought to be ejecta from a large major impact basin impact called the Imbrium impact. You can see these bright layers in the walls of this channel. These are rocks, bedrock that's exposed within the channel. So these channels were carved by very low viscosity lavas, so very hot mafic lavas that flowed over the surface. Just let this keep going, get a better view here. And this is all, this is, a simulation that's put together, but, this is not kind of out of somebody's imagination. This is all actual LRO data that's just put together in this 3D view, but it's all data that's collected from orbit, even though it looks like we're down on the surface. So we try to give you as much of an astronaut's eye view as we can. But if you were on the surface on Apollo 15, this is with Dave Scott. This is not too dissimilar from what you might have seen. So as we think about exploring the moon with humans again in the future, one thing we have to worry about is the sun and radiation. Excuse me. And so we've been thinking about how we can protect astronauts if there was a large solar flare, for instance, that might send out a deadly amount of radiation. And one thing that's a really good insulator is actually the lunar soil and lunar rocks. And so one idea that's been suggested is if we were exploring, say, the mare, which are these huge flood basalt deposits. If you look up at the moon on a full moon night, the dark areas are these big flood basalt deposits. If we're exploring the mare with humans, for instance, we've seen these pits, and we could potentially use these pits as radiation safe havens if, in fact, those pits extend and have overhangs, and they extend like this into caves below the surface, just like pits, in the Big Island of Hawaii do, where they're exposing lava tubes underneath. So a lot of work has actually gone into trying to identify these types of pits and map the characteristics of the bottoms of these pits. I've actually explored lava tubes and pits in Hawaii as part of some of my own geologic field work. These are not easy areas to explore. They're very rocky. It's kind of treacherous terrain, so they're not by any means easy to explore or set up a habitat in, for instance. But they could be potential emergency safe havens to protect astronauts from dangerous radiation. So one thing we want to do, if we are actually seriously considering this, is try to understand the temperatures at the bottom of these pits. And one way we can do that is by using data acquired by LRO's Diviner instrument, which, remember, it's like this, it's a really fancy thermometer, and we can measure the infrared signal coming off the surface. We measure infrared energy as essentially heat energy, and we can use those infrared measurements to model surface temperatures using that takes into account topography, using these kind of 3D physics models like you see here. We can build up 3D models of the topography and then model the temperatures. So these lunar pits, and this example here is a 110-meter pit in Mare Tranquillitatis, Sea of Tranquility. It's smaller than Diviner's footprint, which is 180 to about 500 meters across. And so that's why we have to use these thermal models, because we can't directly measure the temperatures of the surface. But our modeling predicts very complex thermal behaviors in the interior of these pits, and they remain warmer than the surface for much of the day. What you're looking at here, this plot shows these are what we call diurnal temperature curves. And so this is from midnight to midnight, temperature in Kelvin. And so you can see at night, we're at 150 Kelvin. And so 0 degrees Celsius is 273 Kelvin. So we're, minus 120 degrees Celsius at night at the bottom of these pits. During the daytime, we're up to more than 400 Kelvin at the bottom of these pits. So that's hotter than the boiling temperature of water. And temperature goes back down around sunset, back down to kind of, sub, 200 Kelvin. And so we have extreme temperature environments. So we have to build hardware, spacesuits, if we're actually going to plan on exploring these places, that can withstand those temperature extremes. And the environments at the bottom of the pits are much more extreme even than the environments at the normal lunar surface. We can actually measure how these change over time, and what we've kind of been able to figure out is that these pits are warmer than the surface because of what we call black body cavity effects. Black bodies are, this takes you back to your physics 101 classes, in college, if you can remember back then. These black bodies are theoretical materials that absorb all incident light upon them and then re-emit that light at lower wavelengths typically. And so these cavities basically act as black bodies. They absorb all that incident light, they heat up, and then they re-emit an infrared radiation. So what's essentially happening inside these pits is that you're getting a greenhouse effect. So they're absorbing light, they're re-emitting light, and it almost works exactly like Earth's atmosphere does when it absorbs radiation and then heats up and then re-emits it to give us our greenhouse effect. So the temperatures of these pits are dependent on the material that's composed of them. they're dependent on the albedo, so how dark or how light the material are. So just like if you've ever walked on barefoot on a beach parking lot in the middle of the summer, right? That blacktop, super hot because it's dark and it absorbs all that solar light. You can maybe find a little respite by standing on one of those white parking lines, right? That white paint that reflects more light and is cooler. And so depending on whether material is bright or dark depends on whether it gets really hot or can reflect more light and stay cool. So it's dependent on the material, and it's also dependent on whether that pit extends far underneath the surface. So these pits are warm, and diviner data tell us that these materials are probably mostly rocky. And so if we actually wanted to explore these with either robots or humans, we have to deal with a lot of rocks, which complicates things. Whenever we want to send a rover to Mars or the moon, we actually have to worry about how many rocks there are and whether we can navigate around them or not. And so the diviner data are telling us that the temperatures of these pits are actually most consistent with rocky material. And so future instruments, if we actually want to figure out, what's going on in more detail than that, we actually have to have instruments with bigger telescopes on them that give us a better spatial resolution that can resolve those features in detail. I'm actually working with colleagues at other universities to build instruments that could give us kind of meter or 2 meter scale temperature measurement resolution that would actually do this quite well. We just got to, pitch it to NASA and have them fund it and then send it to the moon. Easier said than done. All right, switching gears, I want to talk about irregular mare patches because these are some of the weirdest areas on the moon. So the INA D, if you're like a backyard astronomer, INA is actually kind of like a famous feature on the moon. Now, whenever I look at these features, I actually specifically labeled these as lower areas and higher areas because the way my eyes see them, it's always reversed. I always see these smooth areas as kind of depressions and these in these rough areas as elevated. But in fact, it's the opposite. These smooth areas are elevated and these rough areas are depressions. If you're having a hard time seeing it that way, you might want to try actually tilting your head upside down or turning your computer upside down, because sometimes when you change the point of view where you think the sun is coming from, that can actually help flip things around. But the basic idea for these units in INA, Mascaline, and Sausignes is that we have these very, very smooth areas that have we see a few craters on them, but there's actually relatively few craters in these areas compared to most areas of the moon. So there's a bunch of these all over the lunar surface. They all occur in the mare. So we call them irregular mare patches. They all have basaltic compositions. And because they have very few craters, some scientists infer that they're very young. So planetary geologists use the number of craters as a measure, as a relative dating technique, essentially. Just like on Earth, we use fossils in sedimentary rocks as relative dating techniques, we can use craters on planetary surfaces as a measure of essentially the time stratigraphy. And so it's basically a principle of superposition thing, right? So the more craters a surface has on it, the longer it's been around to accumulate those craters. So by inference, a young surface would have very few craters on it just because it hasn't been around long enough to accumulate a lot of impact craters. And so the models that some planetary scientists have developed based off of the sizes and the numbers of craters for these deposits suggests that these might be very young, like less than 100 million years old. And we really don't have a conceptual framework to understand that. The moon is a lot smaller than Earth. Everything, that interesting that occurs on Earth in terms of geology is basically plate tectonics and volcanism, and it's driven by that. Sedimentation, if you're a sedimentologist, right? Even that is driven by mountain building processes and plate tectonics. Plate tectonics and volcanism are driven on Earth by Earth trying to release its interior heat, right? The moon is much smaller. It got rid of its interior, most of its interior heat a long time ago. And so volcanism is supposed to have shut off, about, the youngest, really good ages we have for, basalts on the moon are about 2 billion years old. So we think, the moon probably has not been volcanically active for more than 2 billion years, but yet we see these units that might be less than 100 million years old. And we honestly have no idea how that could be the case. Right? So it's a fundamental mystery that is still being debated in the scientific community, and we're still trying to figure out. Another thing we're trying to understand is how the typical lunar surface material forms. What the astronauts saw when they landed on the lunar surface was that everything was covered in dust, and everything has this kind of fine-grained, gritty material. You can go to the Smithsonian Air and Space Museum and down in DC if you ever get the chance. I highly recommend it. They actually have some of the Apollo spacesuits there. And what you'll see is that they don't look like movie or TV spacesuits. They're not these bright, gleaming white things. They are filthy. They are covered, they're gray, and they're covered in this very fine-grained dust. The lunar surface is very dusty because it's been pummeled by impacts over billions of years, and the crust hasn't been recycled and relithified like by geologic processes like we have on Earth. So we want to understand the timescales over which this type of thing happens, and we want to understand the rate at which it occurs. And it turns out the way we can start to understand that is by measuring the temperatures of craters on the lunar surface and crater ejecta. So what you're looking at on the left is a young crater on the moon called Chappie Crater. It's only about 1 kilometer across. It's about the same size as Meteor Crater in Arizona. And it has this very distinct and bright ejecta pattern. This is the material that's thrown out by the impact. And what you're looking at on the right is that same crater, but notice the difference in scale bars. Here you're looking at a 1 kilometer scale bar. Here you're looking at a 50 kilometer scale bar. Associated with this crater, the middle of the crater is red in this map. And what you're looking at, the colors in this map are a temperature map. So the red areas are hotter and the blue areas are colder. This is a nighttime temperature map. So at night, it turns out that rocks are warmer at night and dust is colder at night. This is the same thing is true on Earth. And it's simply because of a material property we call thermal inertia. So coarse-grained rocks or large rocks, they absorb solar radiation and they take longer to heat up during the daytime, and they take longer to cool off at night. And so the middle of this crater here has a lot of rocks around it, and it's blocky ejecta, and so it's warm. But what you're looking at in the ejecta surrounding this area, it's actually a few degrees colder than typical lunar regolith around it. And we're trying to understand exactly why that is. And what we found by measuring new craters on the surface of the moon, in fact, go back to 11 slides ago or whatever, where we showed you a new crater forming. These things are, all of these craters are 2 to 10 degrees colder than typical regolith, all these ejecta patterns. Basically, every new lunar crater that's big enough for us to measure has these ejecta that are colder than everything else, that extends out 10 to 100 crater radii. And some very smart people have made some thermal models based on the density of the regolith. And what they figured out is that these colder temperatures are consistent with a fluffing up of the upper 10 or so centimeters of the regolith. And so it's not the result of thick deposits of new material being flown out or modification of this material by the ejecta, but rather we think maybe the shock wave from the crater kind of fluffs up the material, makes it less dense, and therefore it cools off faster at night. Now, the other thing that's really neat is that we found out that, and we've been able to infer based off of measurements of lots of these craters, that these cold spot anomalies look to fade on timescales of about 100,000 to 1 million years. And so this gives us kind of the first timescale for regolith modification, right? So it takes about 100,000 to 1,000,000 years to go from this cold spot, regolith to normal lunar regolith. So that's kind of the churn rate of the lunar surface to generate basically what looks like typical lunar soil. It's 100,000 to 1,000,000 years. So these things have been found on all over the moon, and we've found them basically for every recent impact that's 30 to 70 meters across. I don't want to belabor this too much, but I just want to point out that these appear to be kind of a fundamental part of lunar impact cratering, and they give us a witness plate to investigate the onset of regolith modification and how the lunar soil, fundamental material at the surface of the moon changes over time. That's pretty cool. And we get all this information from temperature measurements of craters, which is kind of an indirect way to get at it, but it's pretty neat. Okay, want to talk about one more kind of really neat result from LRO before I start talking about what we're kind of looking at in the future. And that is what I'll just call highly silicic materials on the lunar surface. Now you're looking at this color map here, which is a map from the Diviner Lunar Radiometer instrument again. This is not a temperature map. This is actually a composition map. We're measuring a property of the lunar surface called the Christensen feature, which is an infrared spectral feature. Longer wavelengths. Now we're looking at here, this scale bar is the wavelength of that feature in microns. And so we're measuring infrared light that's much longer wavelength than our eyes can see. Our eyes are sensitive to light between about 400 and 700 nanometers. Here we're looking at light between about 7.8 and 8.2 microns. And this feature corresponds very well with the average composition of the lunar surface. And so everything that's red here is the mare. These are the dark flood basalts that cover much of the near side of the moon. The blue areas, these are lunar anorthosite. These are the lunar highlands that are anorthositic in composition. And then this area that's kind of down here near the South Pole, this is what we call the South Pole Aitken Basin. It's kind of intermediate in composition. Some of these areas that I've circled are like really, really blue in here. And these indicate compositions with even more, a higher SiO2 composition. And these are the names of some of those features. We've inferred based off Diviner data that they are granitic to rhyolitic in composition. Now, this is really interesting, right? Again, I'll do a comparison with Earth. On Earth, granites and rhyolites form due to the direct action of plate tectonics and crustal recycling, and when we add water to the magma. Now, the lunar interior likely has less volatiles than Earth's. It probably has some, and we know that the moon's never had plate tectonics. And so we have to generate these highly silicic rocks in the absence of plate tectonics. And so we think likely what's happened is secondary melting of the highlands crust to basically melt some of that crust. You get fractional crystallization, which results in the formation of these rocks. Oops. Here are a few of these features. Here's a big volcano. Here, in both of these features, kind of the reddish colors correspond to these high silicic compositions. This is about 25 or 30 kilometers across here on the left. That is a big silicic volcano. Other features might have more intermediate, like andesitic compositions, but we're not quite sure about that. We need better data from a new generation of spacecraft to tell us that. Some of these are, these light tone materials occur in areas that potentially indicate subsurface plutons of large granitic bodies, right? So it's not just these small little features we see at the surface. We actually have evidence by craters poking through the surface or these massifs being exposed at the surface, suggesting much larger subsurface granitic compositions. And again, we have very little idea of how these form, but we're going to try to find out. So NASA has instituted a program called CLPS, Commercial Lunar Payload Services Program, where NASA is paying private companies to build spacecraft to land scientific payloads on the lunar surface. NASA decides where they're going to go. They basically hire these companies as ferry rides to the lunar surface, and then scientists like me get to compete through a proposal process to send scientific payloads to the lunar surface. This area, the Gruithuisen Domes, is one of the sites that's chosen for landing a small rover in 2025. So for a good portion of last year, for about 6 months last year, I worked with a large team to put together a proposal, a $30 million proposal to land a payload of instruments, including infrared spectrometer, ground penetrating radar, gamma ray neutron spectrometer, that would rove on the surface of this rhyolitic dome, make chemical and mineralogical measurements, take high resolution stereo imagery of the surface, and tell us how they formed, how they evolved over time. So there were about 15 or so teams competing here, and we're actually going to find out next month who won. And so I'll either be very happy or very sad about this time next month. But either way, whether it's my team that goes here in 2025 and figures out how these domes got here and won, that's going to be awesome. If not, then I know some of the competitors, and they'll do a great job as well. But we'll have a fundamental new understanding of lunar volcanism and how these kind of exotic compositions formed on the moon. So it's going to be really, really exciting time for lunar exploration coming up. So I'm super excited about this Gruithuisen Domes mission, but NASA has spent a lot of time focusing on the South Pole of the moon since day one. It's a really important target. There's craters at the South Pole and at the North Pole that are permanently in shadow. They haven't seen sunlight for billions of years. And for that reason, they're super cold. They are so cold, they are likely the coldest areas in the inner solar system, 20 degrees above absolute zero. So they actually act as cold traps. So any volatiles that are bouncing around the surface of the moon or in the lunar atmosphere can get trapped in there. And that includes water. And so for that reason, we could potentially use water as a resource on the surface for our exploration needs. The South Pole is now the main target for NASA's crewed human exploration Artemis program. It's going to also be the target for several of these CLIPS missions. LRO has been focusing on understanding the moon and the pole from day one, and specifically these craters that are in permanent shadow. So show you this movie here. I won't show the whole thing just because it's a little long, but this is all LRO data again. We're going down to the South Pole. You can see these craters right at the terminator. The moon does not rotate on its axis like Earth does, at an angle like Earth does. It's basically straight up and down. For that reason, these craters bottoms of these craters never see sunlight. And the rims of these craters are almost in permanent light all the time. So you have areas that are in permanent sunlight, and we have areas that are in permanent shadow. And then we have these other areas that are in shadow some of the time and in sunlight some of the time. Now, the same rules of temperature extremes apply here as they do when I was talking about the lunar pits. These areas, when they're in shadow or when they're at night, are super, super cold. And these areas are very warm when they are in the sunlight. So if we send robots or we send humans here, we have to understand how these shadows change over time so that we can design our rover traverses or our human exploration traverses to stay in the sunlight, especially if we have solar powered spacecraft, right? But more than just the solar power, we have to stay in the warm sunlight so that our instruments in our spacecraft don't freeze. And so these types of maps that have been built up over decades are super important to help us understand how the illumination conditions at the poles change over time. So LRO is really the backbone for preparing for Artemis, and the use of LRO data is going to be critical for finding a base campsite and defining what science will be done there. I want to point out a tool. If you're interested in this and you want to explore yourself, you can go to a website down here called quickmap.lroc.asu.edu, and you can explore all of these different data sets from LRO. You can zoom in, you can zoom out, you can overlay data sets on top of each other. It's basically a lunar GIS, which is really cool. And it allows everyone to interact with these data and support the development of science questions to be answered by future explorers. So it's, for me, this is like something that's really exciting. Okay, so Artemis is, you know, our next generation of lunar exploration. Here are some of the data sets that are in QuickMap, just as an example. Here is just kind of a illumination. Here you're looking at slopes. We have to land in low slope areas so that our spacecraft don't land and tip over. Here, kind of the red slopes are the scary areas. And so you can see how limited some of our landing sites are and how precision landing will actually have to operate on the surface. Let's see here, what's next? Here, you're looking at visibility from Earth. If we want to have a direct line of communication to Earth without a communication satellite, we have to be able to see Earth from the South Pole. And there are certain places we can do that and certain places we can't. Next, here you're looking at illumination. So areas that are red are more illuminated through more of the year than areas that are blue. These white areas are the areas that are in permanent shadow. Here you can see just another example of that dynamic illumination and how it changes over time. And then here is temperature. And so you can see what the maximum surface temperature is in red, and this is all relative. You're looking at a few hundred degrees Kelvin versus basically 20 degrees Kelvin for the blues. So all these areas that are in permanent shadow are super, super cold. The maximum temperatures are only a few tens of degrees above absolute zero. And for that reason, we think that ice can be trapped in some of these areas. And that ice is super exciting because it's a potential resource that we could exploit on the surface. You can see how temperatures change over time as well with season. Here you can actually see the scale bar for some of these temperatures. So these are the summaries of the minimum, maximum, and average temperatures over the course of a lunar year. And you can see these purple areas, these are the permanently shadowed areas. Those are, you know, again, just a few degrees above absolute zero. Super, super cold. Okay, so LRO's been in orbit for more than a decade. Every 2 years, NASA makes us submit a new document or a new proposal to say what we're going to do for the next 2 years, so that, you know, they can make sure that taxpayer funds are spent well, and we actually have a plan what we're going to do. So we submitted our 5th extended mission proposal on January 18th. It's being evaluated now, and we're working towards a few specific science themes. One is volatiles, and that's primarily water and interactions with the space environment, understanding better regolith and cratering, and volcanism and the lunar interior. You know, if we can have a better understanding of volcanic materials on the surface, that's a direct measure, or say really an indirect measure of the lunar interior, right? And then we can provide real-time support for other missions, including these robotic commercial lunar payload services missions and Artemis. Okay, so that's it really. I just, want to say, I'm very excited about the future of lunar exploration. We live in very exciting times for understanding, increased understanding of the solar system. The next decade of lunar science will be one of profound discovery, a lot of excitement, and LRO is going to be leading the way. So, I'll just, let this movie play, and I'll be happy to take any questions if there are any.
Thanks, Tim. This was very fascinating. I have a question from earlier on. You showed the 2 images of the pre-new crater and post-new crater impact. Has that ever actually been, captured on film, like an actual impact as it happened, or is it always the after effect that's seen?
That's a really good question. So far, what we have seen are basically before and afters. But there are specific phenomena called lunar flashes that have been observed from Earth and also observed with the spacecraft at low spatial resolution. And these are, you're looking at the moon and you might see like a little bright dot that's instantaneous, essentially. We hypothesize that those are impacts happening kind of in real time. So we think we've observed real-time impacts happening on the moon, but not at the super high resolution of the LROC camera.
All right, thank you, and good luck to your team. I hope you guys do win. If
Oh,
anybody
thanks.
else, if anybody else does have questions, please feel free to unmute yourself or type them in the chat box, and we'll read them out loud.
Dr. Glotch, this was wonderful. I just remember seeing the Hadley Run when I was a kid on the TV,
Yeah.
and just the resolution there, it was a downer because they really wanted us to see it. It was like a big thing. It was a major deal, and they had the rover and everything, but you couldn't see any of the scale. It just everything looked like it was covered in talcum powder, and so you couldn't tell. They're telling this is like a half a mile deep, and it just looked like a ditch. But
Yeah.
anyway, what you just showed there, I mean, oh my God, it was just amazing to see that kind of relief and that resolution.
Yeah, I think the astronauts did have a hard time with scale, and when you don't have useful markers that you're used to seeing, it can be really hard. And I know I have a bunch of friends who are geologists who have been to Antarctica, or or glaciologists, and they have the same types of problems. When you don't have markers on the horizon, it can be really difficult. And so I mean, I've heard anecdotal stories of folks on a glacier, and they think they're seeing a snow rabbit that's relatively close, but it's actually like a polar bear that's far away, or vice versa, and it's almost impossible to tell. But yeah, one thing that these data really give us, these kind of 3D oblique views give us, is that sense of scale that's really wonderful.
Also, was one of the patched areas what Neil Armstrong had mentioned about some sort of lights, and that's on the Science Channel, so I don't know how much credibility it is, but supposedly he did report seeing something, and it showed something that you had showed in the beginning for one of those elevated patches.
Yeah, so I think what Neil and Buzz saw on their way down was ejecta from the nearby crater. There isn't one of these irregular mare patches particularly close to the Apollo 11 landing site.
Okay, thank you.
Sure.
Good luck with your proposal. Can't
Hey,
wait to
thanks,
see
I
what
appreciate
else you come up with. This is wonderful. Thank you.
Thank you. Appreciate it. Fingers crossed.
So maybe I missed this in the beginning of the presentation, but the orbiter, in Earth time, how long does it take for it to make one orbit around the moon?
Oh, I didn't say that actually, so you didn't miss that. I didn't say it. It's like a few hours to go around.
Okay.
To do one orbit around the moon. But what it does is for every orbit, its orbit precesses, which means it kind of shifts slightly every orbit about where it is. And when it does that, it actually changes what it views as like the local time on the surface, right? So over time, it might be looking at the surface at noon, where it's going to be really warm, and then on the other side of the moon, on the dark side, on the far side, it's night at midnight. But as it orbits around and it kind of goes around as its orbit precesses around the moon, that time shifts. And so some of its orbits, it's looking down at the surface when it's noon. Some of the orbits, it's looking down at the surface when it's 3 p.m. Some of the orbits, it's looking down at the moon when it's 6 p.m. And so based off of those looking at the surface at different times of day, we can build up those temperature maps showing how the temperatures change over time.
You say the day isn't actually 28 days on Earth. It's
one lunar day. Yep.
Okay. So
Same.
noon is 14 days from dawn, from sunrise.
That's exactly right. Yep.
Yeah.
Same altitude, or is it an elliptical orbit?
So that's a great question. Its orbit's actually changed over time. So for a while, it was in a 50-kilometer circular orbit. And that's when we got our highest spatial resolution data. Basically, the closer you are to the moon, the bigger things are going to look, right? But it takes a lot of fuel to maintain that orbit. And so a decision was made, I don't know, 5 or 6 years ago to make the orbit bigger. And so it was in a 100-kilometer circular orbit for a while. And now it's in an elliptical orbit where the lowest altitudes are around the South Pole and the highest altitudes are around the North Pole. And so every time it comes very close to the surface, it's right around the South Pole. And so we're getting very high resolution images and temperature data right around the South Pole where we're going to be sending astronauts. And we have something like 6 or 7 years worth of fuel left. And so as long as nothing goes wrong, we could stay in orbit for another 6 or 7 years.
That looks like the roughest part on the whole moon, though. You look at that.
Yeah, no, it's
The
scary.
worst place
Yeah,
to go.
yeah, absolutely. No, it's a
Wow.
very high slopes. And so, you know, a lot of the precision landing, you know, a lot of the technology that's being developed is for precision landing, you know, within, you know, kind of 100-meter landing ellipse. If we can do that, then we'll be safe. Okay.
Anybody else? No? Okay.
Thank you very much.
That was awesome. As I said in the beginning, I knew this wasn't going to disappoint. That's some good stuff. Thank you
Thanks.
so much.
Thanks very much. I appreciate it.
We have, if anybody wants to hang around, Olivia Miller, one of our board members, was kind enough to put together some trivia about the moon. We have a few slides about that I'll share with you. They're hard questions. I'll just leave it there and let's see. I should be sharing my screen now. Hopefully. Yeah, I am. Okay, so let's see if we can get a question up here. First question. Who first proposed the prevailing theory for the formation of the moon? And there's several individuals, all last name Darwin. We're not doing a poll this time, so I'll just let you think about it for a minute here or so, less than a minute.
And I'm embarrassed. I don't know this.
I don't know where she got these from. These are hard. I think I know the answer to one, and the answer is George Darwin. So we'll have to look that up. Next question. In the giant impact hypothesis, protoplanet collided with proto-Earth to form the Earth's moon, which is closest to the size of that protoplanet. This one I knew.
At least I know one. That's good.
The name of that was Etheria. Was that right? Is that right? No.
Yeah.
Yeah, Theria. Thea. Right. All right. And the answer is Mars. Mars is smaller than Earth, but must have been pretty ugly. All right. Question 3. How long ago was the giant impact believed to have been? And the answers here are anywhere between 1.3 and 4.5 billion years ago. And the answer to that is 4.5 billion years ago. Quite some time.
And we have a rock from the surface of the moon that tells us that essentially. It's called the Genesis rock that was acquired from the Highlands. It's a 4.5 billion year old anorthosite. So that's essentially the age of the moon, and it's almost the age of the solar system. It's pretty cool.
Is it based off of just one rock, or do we have multiple points of evidence on that?
So that was the first one we got. We have a few other rocks that are about that old, and we have multiple chondrite meteorites that we can date the oldest pieces of those that are 4.56, 4.57 billion years old.
All right. Next question. How far is the moon at perigee and apogee, respectively? And you've got distances here in kilometers. That'll throw me off.
Way to go, Olivia. We're American here.
Well, the failed metric system for those that are old enough who remember. Well, the answer is 362 and 405 kilometers. All right, question 5. Which is the hottest estimated temperature at the moon's equator?
If you were paying attention to my talk.
I'm going with number 4. Let's see if I'm right. Oh, I am. Okay. There's 10 questions. Number 6. Which is the correct order of the atmospheric elements of the moon by volume? Whew, that's a tough one. And the answer is helium, argon, neon, and sodium. That atmosphere is what is it? 0.1% of the Earth's density. Is that right?
Oh, it's way less than that. It's
Way less
something
than
like
that?
it's something like 10 to the minus 15 bars or something like that. It's like more vacuum than we can easily make in the lab with like turbo pumps. It's almost the vacuum of space. It's very, very tenuous. In fact, it's so diffuse that we've actually been able to make measurable changes of the lunar atmosphere just by having our spacecraft in orbit around it exhaust.
So are these proportions reliable and determined through what, spectroscopy?
Yep, that's exactly right. Yep.
Hmm.
Yeah, so we
Neat.
measured them, and in fact, we had that one of the missions I mentioned, LIAPG, was at the very beginning, was specifically designed to measure the composition of the atmosphere or the exosphere before this kind of knowing that we were, us and China and India and lots of other countries are going to be sending lots of spacecraft, likely changing the atmospheric composition. So we wanted to send at least one spacecraft to measure the atmosphere before we did all that stuff.
You mean changing the atmosphere due to rocket exhaust?
Exactly right. Yep.
Wow.
That's how tenuous it is. Just a few spacecraft can actually change the composition just through the rocket exhaust.
Huh.
Yeah,
Neat.
we'll mess it up.
Yep.
Yeah. No doubt.
Solution.
All right. Question 7. Which are the 3 most common minerals at the lunar surface? Well, let's see. Silica, aluminum, and lime. Huh. Neat. I wouldn't have guessed that one.
Yeah, well, the calcium is really, I mean, these are just like the weight % oxides, right? But the calcium is in, well, the anorthosite is
Yeah, the anorthosite.
calcium plagioclase. And then there's
Right.
lots of calcium-rich pyroxenes in the basalts as well.
Okay, fair enough. Makes sense. Question 8. Which surface elements vary the most between the highlands and the Maria? I think you just gave that one away. All right. Yeah. Okay. Question 9. The moon previously had a magnetic field close to that of the Earth. How long ago did the dynamo stop operating? Well, that certainly would be when it lost a lot of its heat. And the answer is 1 billion years ago. Okay, we'll wrap this up. Question 10. Which lunar Maria has the largest diameter at 2,568 kilometers? I'm going with 3, Marimbrium, but I can't. How do you pronounce that? Fecunditis?
Fecunditatis.
Fecunditatis. All right. Let's see. Oh, wrong again. Okay. I think that's it. Well, all right.
Those are good questions, Olivia.
The hard questions, Olivia. Holy
I'm
cow.
sorry, I didn't mean to make them that.
No, they're good.
Good job, Olivia.
It's good. Yeah, good job.
I learned a bit about the moon doing this. I thought, I'd try to throw in some more, added facts onto it. But thank you, Tim, for adding some commentary to it. I appreciate it.
Yeah.
My pleasure.
Yeah, this was a great session. And again, thank you so much for your time. It was very, very interesting and educational, and you did a great job presenting it. Thank you everybody who came out to view it, and look forward to seeing you next month and the month after, hopefully. So with that, I'm going to say good night and go watch some basketball.
Thanks, everyone. Good night. Bye.
All right, bye-bye.
Bye-bye.
Thank you.